And then this is Mr. Ward. We get this vicious squirrel here. My dog chased him out of the house. He was playing with my computer, so sorry about that. Carlo dropped over to my house this afternoon. He brought the card you guys made out. That was really nice. Whoever drew the vicious squirrel, you pretty much nailed his likeness there. And I don't want to spend too much time talking about how I'm doing, but I don't have any major pains, and should be on track to come back Monday. And whether you want me or not, I'll probably be there on November 30th. But right now, we're going to do some problems, particular upside down roller coasters. And this will be fairly short because I want to also have you work on a few little problems of this type. So let's move on to the first problem. Okay, here's the first problem. You have a guy who goes over the bottom of a loop in a roller coaster, and he's upside down, head down. He's going so slowly that he'd fall out if it weren't for the shoulder harness. Draw the free body diagram and find an equation for F normal. Okay, well, let's just do that. And this will be, you don't have any numbers, so we'll just do a symbolic solution. This will be his mass, and this then will be his weight, mg. And remember, he's going upside down under this coaster. So what that means is that the radial force has to point toward the center of the circle, which would be down here somewhere. So what that means is that the upward force has to be smaller than mg. And what would we call that? Well, that's a little tricky. But what we're going to call that right now is the normal force. And that might not sound like it makes sense to you, but if you think about it, it's pushing, it's a surface, the shoulder harness, pushing upward on the guy's shoulders instead of when you sit in a chair, it pushes upward on your butt. In this case, it's pushing up on his shoulder. So it's kind of like standing on your head in this situation. Okay, so let's write our equation. Sum of the forces in the y direction equals ma in the y direction. Excuse my voice. I've got a couple things going on here that are giving me a sort of a hoarse voice, but hang in there. Okay, so we have, since the acceleration is going to be in this direction, a radial, then we would say mg minus fn equals may, which is actually ma radial, and that would be mv squared over r. So the normal force here is going to be equal to mg minus mv squared over r. And that makes sense because this says take the guy's weight and subtract off some number, and that number would be the radial force. And that will give you the normal force, which of course would be then smaller than his weight. If that doesn't make sense to you, put a little question mark there, and we can talk about that when I get back. Okay, so what are we going to do with that? Well, we're just going to leave it here for a while, and then we're going to do another problem. In this case, what we're going to do is we're going to have him go, so now he goes faster just enough. Okay, let's try that again. Just enough that he won't fall out, even without a harness. Say, can you do that? Sure you can. And when I get back, I'll show you a demo of that. But for now, let's just do the problem and see what happens. So what this says is he's going to go over the underside of the roller coaster. And now he's going faster. So the radial force is going to be bigger than it was up here. Notice the radial force up here would have to be smaller than his weight. What happens in this situation, he also feels weightless. He isn't really weightless, but he feels weightless. He feels like he's in free fall. What that means is the normal force equals 0. So this is a special case. And we find that this is the direction of the radial force, or I'm sorry, I should be putting here, this is the direction of the radial acceleration for the center of the circle. And as I drew up here. So what does that equation come out to be? It's a little simpler. We just say the sum of the forces in the radial direction equals ma radial. Plugging them in, what is the only force in that direction? mg. What is the radial acceleration? v squared over r. So what we find out here is that v squared equals g times r. Now you might remember this before. This is the speed that he went over the top of a hill, and it made him feel weightless. I think we did that one. If not, we'll take a look at that again later. So he feels weightless. Now I'm going to do a number of demonstrations when I get back to make this a little clearer for you. But for now, I'm just asking you to buy this and see if you can make sense of it, and we will get into it a little deeper. Now let's do another thing. So on the first one, he was not going fast enough. He would have fallen out. Now he's going just fast enough not to fall out. And now he goes even faster. Then he needs to go to not fall out. So find F normal. Again, these are a little bit trickier, but hang in there. Okay, so this will be your track, and this will be our guy going around the track. This will be mg. Now think about this. He's going around a turn, the same turn that he was before. He's going really fast now. So what kind of a force do you need to keep you in a tight circle like that? You need a larger force. So you need an even larger radial force. Now how do we get that? Now we put the normal force on here. And why is that? Because we need a larger force, and the question then would be, what causes it? What causes that large force? You say the normal force, yeah, but what thing causes it? Normal force. Okay, that would be the seat. The seat pushes him down. So what we would find here then, sum of the forces equals m in the radial direction equals ma radial, and that would be mg plus fn equals mv squared over r. Therefore, fn would be equal to mv squared over r minus mg. I'm going to creep up to the first problem. Up to the first problem, you see it's mg minus mv squared over r. On this problem, we see it's mv squared over r minus mg. And if we go to the middle one, we find there is no f normal in this problem. So these are the three cases. And there's some very interesting things that happen when you go over a roller coaster upside down in this situation. We're going to talk about that, but which way does this guy feel is up? Oh, I'm sorry, down. The answer is up. It's kind of strange. There's another question. What would happen if he dropped a ball in the coaster car? Answer: move toward its speed. Sounds kind of crazy. Does that mean it falls up for him? Yeah, does it mean it falls up? No. So why does it look that way? Again, it's a little bit complicated to do in a video without an actual movie of what's happening. So we're just going to leave it at this and hope that you think about this and see what you think. I'm going to stop this now, and your proctor is going to give you some problems to try out. They probably won't deal with these last three, or deal with the other ones. And the point of these problems is to see if you can remember how to do these things. So try to figure out problems without looking at notes. That'll be challenging, but that's why you're here. You can figure these out. You might have to look, which is okay, but try to figure them out first before you look them up. So I'm going to cut this one short here today, take the rest of the period and work on these problems. I haven't made the problems up yet, so I'm not sure how many there'll be. There'll probably be about 5 problems, maybe about one of each of the types that you've done. I'll scramble them around a little bit, so you have to just do them in order that they are in your notes. Okay, so this is the last video for class. I'm still going to do the last 3 friction problems. And that'll be another video. I think I'm going to do that. I'm doing this on Monday night. I think I'm going to do that tomorrow because my voice is giving out on me here. So that's it. Thanks for the card and the good wishes, and also for the vicious squirrel. And we'll see you in about a week.